Hello once again, everybody. This is Mr. V. Hill. I'm here to talk to you about the basics of exponents. So we finished up pretty much all that we're going to do with linear expressions and linear functions. So now we're going to get into exponentials. And we're not going to do a whole lot with solving exponential equations here. That's going to be left to Algebra 2. But we are going to be doing a plenty of simplifying. And if we remember, simplifying basically means doing all the arithmetic that you can. So of course, if you can do some multiplication, do it. If you can do some addition, do it, and so on and so forth. But this is going to include applications of, first, the distributive property. All right, so if we have something like 3 times the quantity x plus y, we don't know what x is, we don't know what y is, so we don't know what x plus y is, so we can't really do that multiplication of 3 times that thing. Well, yeah, we kind of can, by applying the distributive property here. And saying that 3 times the quantity x plus y is 3 times x plus 3 times y. So the distributive property is actually how we do this multiplication that is connecting the 3 to the x plus y in parentheses. That's one extra bit that we have to do. The next thing we have to also do is combine the like terms. All right, so if we had something like 3 times x plus 5 times x, well, we don't know what 3 times x is because we don't know what x is, and similarly for 5 times x. But we can actually do this addition here. 3x plus 5x is actually equal to 8x. So combining like terms is how we do this addition. And of course, we also have to combine like factors. And what I mean by that is if we had something like x squared times x cubed. Well, we don't know what x squared is because we don't know what x is, and similarly for x cubed. But here we have 2 factors of x multiplied together. Here we have 3 factors of x multiplied together. So all total, we have 5 factors of x multiplied together, where this is x to the 5th. So that's what we are calling simplifying so far. Now we're going to have to do a few more things with exponents. And exponents basically is, of course, an exponent is really nothing more than a repeated multiplication. Right? X squared meant we have 2 x's multiplied together. It's like 3 to the 4th is equal to 3 times 3 times 3 times 3. 4 3's all multiplied together, which is, of course, 81. And that works for natural number exponents. But what about other kinds of numbers? For instance, what if we have an exponent of 0? We've already talked about this before, but according to this, if we look at an exponent as a repeated multiplication, what in the world does it mean to multiply 0 3's together? So that's the question. And it basically, it's pretty simple to figure out what it has to be. If we just look at a table here, say x on the left-hand side and, I don't know, 3 to the x on the right. If we let our x's be 0, 1, 2, and 3, well, we're trying to figure out what should go here. But here, we plug in our x value of 1, 3 to the first. Well, that's 1 3 multiplied by, obviously that's 3, right? Here, 3 squared, or 3 to the power of 2. Well, that's 3 times 3, 9. 3 to the power of 3, or 3 cubed, 3 times 3 times 3, 27. Okay. So we just look at a pattern here. How we get from 3 to 9, well, we multiply by 3. How do we get from 9 to 27? Well, we multiply by another 3. Let's think about going the other way. to go from 27 to 9, well, you divide 27 by 3 and you get 9. Similarly, if we divide 9 by 3, we get 3. If we continue that pattern, 27 divided by 3 is 9, 9 divided by 3 is 3, 3 divided by 3 would be 1. So 3 to the power of 0, well, that should be 1. I mean, that's the only thing that really makes sense there. And that's how we're going to define it, is that a to the power of 0 for any real number a, that is going to be always equal to 1. And that's for any real number except 0. 0 to the 0, well, that's something else entirely. That's what we call an indeterminate form. At least in the string that we're going with in your high school curriculum, taking us up to calculus. But in order to really talk about this, we do need some ideas from calculus. So we don't need to worry about that for right now. For right now, all we need to know is that if you take any number other than 0, you raise it to the power of 0, that has to be 1. But what about negative numbers? We need to know how to deal with those as well. And actually, that's not too hard either. We just take that same table and extend it a little bit more. Maybe down to negative 3. All right, I said here that 3 to the power of 0 has to be 1. Of course, 3 to the first is 3. 3 squared is 9. 3 cubed is 27. But let's extend this back. So we divided 27 by 3 to get 9. We divide 9 by 3 to get 3. We divide 3 by 3 to get 1. So 3 to the power of negative 1 should be what we get when we take 1 and divide it by 3. 1/3. Or, of course, dividing by 3 is the same thing as multiplying by 1/3, so 1 times 1/3 is 1/3. Extending that one more step, 3 to the power of negative 2, we should get that by taking this 1/3 and dividing by 3, or multiplying by another 1/3. And 1/3 times 1/3 is 1/9. Do that one more time, and 3 to the power of negative 3 should be what we get when we take 1/9 and multiply it by another 1/3, and that would be 1/27. Okay. And we might want to look at this a little bit differently, just so we can generalize this a little bit. 1/3 is, of course, 1 over 3 to the power of 1. 1/9, well, that 9 is actually 3 squared. And here, the 1/27th, 27 is actually 3 cubed. And so if we just want to generalize this, I mean, that's what it has to be if we follow this pattern backwards. And so what we're going to do is we're going to define a to the power of negative n as equal to 1 over a to the power of n, for a not equal to 0. Because, of course, 0 to any power would be 0, and 1 divided by 0, well, can't do that. Or if we really wanted to, if we want to think about it in a slightly different way, this would be equal to 1 over a to the power of n, right? Because each of these things, 1 over 3 to the first, or 1/3, would be the same thing as if we take 1/3 and raise it to the power of 1. That's not simplified, though, because of the parentheses. So we still have to do a little bit more. But it's not too bad to think about it in that way. 1/9 is actually 1/3 squared, and 1/27 is actually 1/3 cubed. So sometimes it's going to be more beneficial to think of it this way, other times it's going to be more beneficial to think of it this way. But how this is going to apply to our situation is that we're going to add one more rule to simplifying. So now, in addition to what we had before of doing all the arithmetic, applying distributive properties, applying combining like terms and combining like factors, we are also going to have no negative exponents. let's do an example, a pretty simple one. Suppose we have something like 2 over m, and we're going to raise that to the power of -4. We're going to think about this in a couple of different ways. First, by just applying this idea, that anything raised to the power of -n is equal to 1 over that thing raised to the power of +n. So here we go. We've got this thing in parentheses, raised to the power of -4. So that would be the same thing as 1 over that same thing in parentheses, raised to the power of +4. Now we can do some more arithmetic here in the denominator, because we know what raising something to the power of 4 means. So this is actually equal to 1 over, well, we need 4 copies of this thing in parentheses all multiplied together. And that's nice, because now, of course, we know how to multiply fractions together as well. Just multiply all the numerators together and multiply all the denominators together. So this is going to be 1 over, well, the numerator is 2 times 2 times 2 times 2. That is just 16. And on the bottom, m times m times m times m. That's 4 m's multiplied together, or m to the 4th. And don't forget your parentheses around your denominator. That's important. And now, of course, we don't want fractions within fractions, because we can actually do this division here. Dividing by something is the same thing as multiplying by its reciprocal. So this is actually equal to 1 times the reciprocal of this denominator, which would just flip it over, m to the 4th over 16. And now we don't really need this multiplying by 1 there, because it doesn't change anything. So this is just m to the 4th over 16. Fantastic. And now we can't do any more arithmetic in here, so that is now simplified. Okay. Well, thinking about it in a slightly different way, if we want to use this idea of really what happens here is this negative sign up in the exponent really tells us to take the reciprocal of the base. A, the reciprocal of A is 1 over A. So we're taking this negative sign, boom, it tells us to take the reciprocal of the base. And that's going to make this little simplification problem slightly simpler. 2 over m to the power of -4. Well, this negative sign tells us to reciprocalize the base, even though one should never verbize a noun by adding a suffix. So the reciprocal of 2 over m is m over 2. We've applied the negative sign in there, so the exponent that's left is just 4. But again, we know what raising something to the power of 4 means. That's m over 2 times m over 2 times m over 2 times m over 2. 4 copies of the base all multiplied together. And now we can do this arithmetic. M times m times m times m on top, which is just m to the 4th, over 2 times 2 times 2 times 2, which is 16 on bottom. And that's the basics of exponents, how to apply 0 exponent and a negative exponent. And so go back, watch this video again, make sure your notes are very, very neat and understandable. Otherwise, you're going to have to answer to this creepy looking lady with a sledgehammer.